So last week we talked about hierarchical Bayesian models, and so that they were very important in observational studies because unlike purely empirical approaches such as multiple linear regression, hierarchical Bayesian models allowed us to tease out the underlying processes. So the whole point of this video is to show that Bayesian thinking has additional applications that extend beyond those very useful hierarchical Bayesian models. I'm going to go over 3 examples. As I do that, don't worry about the details, just focus on the power and flexibility of Bayesian methods. So the first example is that of Bayesian networks, and we're going to start off with a scenario, and the scenario comes from Cherniak, 1991, and the whole idea is that we've got a family, and when the family goes out, they turn on the outdoor light. But sometimes the light may be on even if the family's in, if the family has visitors. And the family has a dog. And if the family's out, the dog is out. But sometimes the dog may be out even if the family's in, if the dog is having bowel problems. Thirdly, if the dog is out and a person walks by, then they're probably going to hear the dog bark. On the other hand, a person walking by may hear a dog barking. It won't be the family dog, it will be a neighborhood dog. So, here's the deal. A person walks by, the light is on, no barking is heard. What is the probability that the family is home? So what we do is we create a network. A network of prior probabilities and conditional probabilities. And we start off with the prior probability that the family is being out, which we set at 0.15. The probability that the dog is having bowel problems is 1%. And then we've got a series of conditional probabilities. So, the probability that the lights are on if the family is out, FO plus, is 60%. The probability that the lights are on if the family is in other words, family out is not true, is 5%. Now, let's think about the situation involving the dog. This is the probability the dog is out if the family is out and the dog has bowel problems. Well, under those circumstances, you can be pretty bloody sure that the dog is going to be outside. On the other hand, what's the probability of the dog being out if the family's in and the dog is doing okay? That's only 30%. The probability of the dog being out if the family's out but the dog is healthy is 0.90. Probability of the dog being out if the family is not out but the dog is having problems, 0.97. And then finally, the probability of a passerby hearing the dog bark, HB, if the dog is out is 70%. The probability of that person hearing a bark if the dog is not out is only 1%. The barking they hear is that of some neighborhood dog. And so the whole goal is to, once again, to calculate the probability that the family's out, given the lights are on and no barking was heard. To do that, what I went was go online to this package called Netica. I took this network, series of drop-down menus, essentially recreated it here, and then put on the data. So the data, are the lights on? Yes, they were. True, 100%. Was a bark heard? False, no bark was heard, 100%. And it automatically calculates the posterior probability that the family is out, which is 50%. It calculates these other posterior probabilities as well, but they are not so interesting. So if we draw the camera back a bit and think about what happened in week 2, when we had Acme Coin Company, and we started off with an 80% probability of having a head bias coin. We got 4 heads in n is equal to 10 flips, and the posterior probability of having head bias coin was 31%. So we're doing a very similar thing here. We're going to start off with a prior probability that the family's out. So we're going to start off with a prior. And then we're going to create this complicated network. Then we're going to get some data. Data is no bark, lights on. We wind up with the posterior probability of the family being out is 50%. So, big picture, Bayesian approaches are really powerful. So we can see, and these are just a couple of papers I found, didn't read them in any detail. Bayesian networks uses a novel tool to enhance the interpretability and predictive power of ecological models. So you can see one application. We look at this paper, it talks about Bayesian deep learning and a probabilistic perspective of generalization. So we can see that Bayesian thinking isn't limited to hierarchical models, that it extends all the way into deep learning and artificial intelligence. So the next application I want to talk about involves loss functions and decision making. And as an overview, where we're going to begin with the posterior distribution provided to us by Bayesian data analysis. Then we're also going to have on hand a loss function. We're going to combine these two things to calculate the expected loss, and that's going to guide our decision making. So to begin, let's think about this idea of a posterior distribution. And if you go back to the globe tossing experiment, when we said there were 5 values for the proportion of Earth covered by water, and there they were, and there was the posterior distribution that we obtained. So the example I'm going to go over is we're trying to decide whether or not to buy a book. And we go online and we see for that book, it's got a number of reviews. 10% of the people gave it a 1-star review, 20% gave it a 2-star review, 30% gave it a 5-star review. Now, at this point, you're going to have to humor me and use some imagination, because what I'm going to say is that for this example of buying a book, we can take these online reviews and view them as a posterior distribution. So in this case, theta, the parameter, is going to be the quality of the book. 1-star poor, 5-star excellent. And the posterior probability is going to be these percentages converted into proportions. So we start off with a posterior distribution. So there's our posterior distribution. And now what we need is a loss function. And here is our loss function. So we've got the quality of the book, poor, fair, all the way to excellent. And we're going to make a decision. We're either going to buy the book or we're not going to buy the book. And what this loss function tells us is the cost that's going to be attained if we buy the book versus not buy the book, depending on the quality of the book. So, in the situation where we buy the book, the best case scenario is if the book is excellent. If we buy the book and the book is only good, then there's going to be a loss because, we bought the book and it's merely good as opposed to excellent. Continuing on, the maximum loss occurs if we buy the book and it turns out to be only a poor book. On the other hand, we may decide not to buy the book. Well, under those circumstances, the least loss is going to be attained if it was a poor book. That would be the correct decision. On the other hand, let's say the book was an excellent book. Well, then there'd be a considerable loss involved because we had an opportunity to buy the book and learn a lot. We didn't buy the book, therefore we attain this loss. So we got our posterior, we got our loss function, and then we combine them to calculate the expected loss. So in week 1, we talked about how do we calculate the expected value for a random variable, and we attain that by taking the value of the random variable, lowercase y, and multiplying by the probability that that is the value of y that will occur when the experiment is actually done, and then summing over all the values of y. So we're going to begin with our posterior. So there was our posterior there. I've just moved it here. And then we've got our loss functions. We've got our loss functions there and our loss functions there. And I've just moved them here. There's the loss function for buying the book. And there's the loss function for not buying the book. And then what we're going to do here is multiply the loss times the probability of theta given data. So if we begin with buying the book, we take the 0.2, we multiply by the 30, we get the 6, the 0.2, multiply by the 25, the 5. We sum that up, and that gives us the expected loss if we buy the book. And then we repeat the process for not buying the book. So we take the 0.2, we multiply the 0, get 0, take the 0.2, multiply by the 15, get the 3, sum it all up, we get 21.5. The loss, the expected value of the loss if we don't buy the book is greater than the expected value of the loss if we do buy the book, and so that pushes us towards buying the book. Now, if we think about this in a practical setting, one could imagine a scenario where one is going to make some sort of management decision. And that's going to affect a bunch of things, and we can represent those by thetas. So the first might be some wildlife population. Second one might be forage quality. And the third one might be some measure of recreation value. So if we have our management decision, we could calculate the posterior distribution of all these parameters. And for each one of these parameters, we could think of, okay, what's the best thing that could happen? And then what would be the cost that would occur if we had less than the best thing happening? We could combine that all together, and that would give us some guide for our management. So the whole idea is another application of Bayesian modeling, Bayesian thinking, is in combining posterior distributions with loss functions to guide our decision making. So the last application I want to go over are packages that written in R that use Bayesian methods in the background. So in week 6 and earlier this week, we looked at some runjags code that used Gibbs sampling to implement Bayesian analysis. The code was fairly complicated to write, but was relatively transparent. So what this section is all about is we're going to look at some R packages that have a user-friendly interface that permit the writing of fairly simple code, but in the background do Bayesian analysis. So in terms of the algorithms, there's many possible algorithms. It's going to vary among the packages and what the packages are attempting to accomplish. The code, as I've said here, is simple. It has the disadvantage, however, we're going to see that it may be a bit opaque. So in terms of what packages are available, in the notes I talked about brms, Boral, RInla, and then I went to ChatGPT and asked it for R packages running Bayesian analysis in the background. And here's some things that show up. Bayesian analysis of count data, Bayesian hierarchical models for ecological data analysis, Bayesian structural equation modeling, Bayesian model averaging, time series using Bayesian methods. So there's a lot of these packages that are available. So now what I want to do is go through an example of one of these packages. I'm going to use BRMS. It stands for Bayesian Regression models, and S stands for stand, which is just a way of doing Bayesian analysis that's relatively analogous to JAGs or runjags. So the data come from Steele and Torrie. It's a randomized complete block design. There are 4 blocks, and there are 4 treatments. These are the data that were accumulated. So we're going to get estimate of the treatment effects in 4 different ways. One is we're just going to take the raw means. So we take check this value, this value, this value, this value, take the average, and that's shown here. We're going to run runjags, and in addition, we're going to look at LME4. And LME4 is a package that many of you may be familiar with because it contains the LMER function that is commonly used for mixed models. And then we're going to look at BRMS that implements Bayesian analysis using syntax that is relatively similar to LME4. And the whole point of this table is to show that irrespective of how we go about obtaining the estimates of our treatment effects, they're going to be exactly the same or pretty much the same for all of these treatments. That allows us to compare kind of the pros and cons of these different approaches. So here we've got the runjags code, and you can see that it's pretty complicated. In contrast, if we look at the LMER function of LME4, it's pretty straightforward, pretty simple code. And the whole idea about BRMS is we've got this BRM function that's going to implement this Bayesian analysis, something very similar to this, running in the background. But the code that we provided, if you look at LMER, there's the data specification, and there's the formula. There's the data specification, there's the formula. So you got a whole lot of folks out there that are familiar with LME4 and the LMER function, and they can just essentially use the same code to do Bayesian analysis. So we can see the obvious advantage of BRMS over runjags in that it has much simpler code. How about what would be the advantage of using BRMS as opposed to LME4? That would be because it's Bayesian, it potentially has more power and more flexibility. And that can be seen in this table from Burkner, where we compare BRMS and LME4. Categorical models, yes, no. Zero inflated, generalized additive, nonlinear models, yes, no. Multivariate, a few, no. Anybody, most of us are going to have to encounter autocorrelated data, yes and no. So the clear advantage of BRMS is the power, the flexibility. However, if we think about things like BRMS that are involved in this section, the issue of opacity comes up. And that opacity can happen in at least a couple of ways. First of all, if we just go back and look at the LMER function, the code here can be pretty tricky. Now, in a very simple randomized complete block, it's pretty straightforward. However, if you've got a complicated design structure with blocks and plots and subplots and repeated measures, it's very difficult sometimes to correctly specify the random effects. And so it's possible to get results that are plausible yet incorrect. The second level of opacity is, how is the Bayesian analysis being done? We spent a lot of time talking about priors. Well, there's no prior specification here, so without some effort, you really don't know how those priors are being chosen. We've got this thing warm up. Well, when we did runjags, we talked about burn-in versus adaptation. So what is warm up? Is it this, is it both? So the whole problem, the whole message that I want to get across is that there's out there just a very large number of packages. And I just chose BRMS as an example. But the whole point is they're powerful. They involve simple coding, but you've got to be really mindful because of this opacity issue, because otherwise it's really easy to get results that are plausible but completely wrong.